Hey there. So today what we're going to talk about is the second part of the geometric optics lesson, which is about spherical mirrors. Last class we were talking about flat mirrors, which is basically a flat, shiny piece of material, and how it reflects and how we are able to predict where its image is going to go and what its image is going to look like. And today we're going to take that a step further by looking at two different kinds of spherical mirrors. So we have two kinds. The first one is called the concave, and the second one is called the convex. So before I get into any of the details about this, let me actually show you a real picture of these two types of mirrors. So over here we have a concave mirror. So as you can see, this lady right here is the object, right? And we're looking at her hand, and this is the reflection of her hand. Obviously, due to the shape of this mirror, we see that the hand's image is greatly magnified compared to the original size. Also, some of the stuff in the background has been inverted. So the wall, the bench, the floor is all upside down. And we're going to look at the reasons why this ends up happening. Let's look at the other type. The other type is called the convex mirror. So we have the same lady. She's holding up her hand, but now her reflection looks a little bit smaller. But one of the interesting things that happens with convex mirrors is that we're able to see a wide field of view of things around it. So this type of mirror is very useful for when you're trying to look around a corner, or you got to have it in your side view mirror in your car if you want to look on the sides where it's kind of hard to see on your own or with the mirror by itself. You would use this type of mirror that helps you see more of a wide angle. So again, this is our convex mirror, and this is our concave mirror. And what I want to show you how to do today is how to look at the ray diagrams and just kind of look at how the optics work for both of these types of mirrors. Here we go. Now, let's start with the concave mirror. So let's say I have an object, all right, a candlestick. Putting it on some flat line, which is going to be our principal axis for our mirror. So let's go ahead and put a concave mirror in front of it. Now, here's the interesting thing that I want to show you about spherical mirrors and why they're called spherical mirrors in the first place. I'm going to take my ruler here and make a circle. Now, the reason that's called a spherical mirror is because these guys are really cut from a spherical shape. So we take our big spherical mold and we cut a piece of it out, and then we build a mirror around it. So that's why it's called a spherical mirror. Now let me show you 2 points for this type of mirror. By the way, this is going to be our shiny side on the left, and the back of the mirror is going to be the right. So I'm going to draw our usual lines that represent the back of the mirror. Let me show you 2 special points for this thing, C and F. So the C is going to represent the center curvature. And the F is going to be called the focal length, or sometimes it's called focal point. Now, the center of curvature is located exactly at the radius of the sphere that this mirror is cut from. And halfway between that is going to be the focal length. So let's say your center of curvature is 5 centimeters. your focal length will then be 2.5 centimeters, right? Exactly half. Now, check this out. Notice where my candlestick is located along the mirror, somewhere beyond the point C. So I'm going to draw two lines. The first one is going to be a line that goes straight across parallel to that middle line. Once it hits the mirror, it will reflect and then go through the focal point, like this. I can draw another line that goes through the focal point, and then it will then reflect parallel to that center axis. Now, I want you guys to pay close attention to the point in which they intersect, which is going to be right here. If you were to do this for all of the light rays that are coming from the candlestick, they will all kind of like intersect at some point, which would be that one that I just drew. So here's what ends up happening. You get an inverted real image. Now, the reason that the image is real is because of this. Let's say that we had a screen, right? A screen could be like a piece of paper or whatever. And we were to place the screen right here. If you were to look at that screen, you would see that the image will be projected onto that screen upside down. Since we could project that image and we could actually see it, it means it's a real image. When we have a virtual image, they always show up behind the mirror. And if you were to place a screen on that point, you won't be able to see anything because there's no actual light going through that point. All right, let's take a look at something else. Let's bring that image a little bit closer. I'm gonna bring back up my center of curvature and my focal length. What ends up happening now? Let's see. Again, I'm going to draw two lines. The first one is going to be through the center of curvature like this. Now, one interesting thing that happens with the center of curvature is it doesn't actually it doesn't really like bounce from one point and then deflect like at an angle. It will always, if the light is going through the center of curvature, it will bounce back and hit through the center of curvature again. So it actually, at that point, gives you a perfectly straight line. Now let's look at another one. A line parallel to that center axis that then goes through the focal length like before. Now take a look over here on the other side. You have another piece that intersects right up here. And again, if we were to do all of the incident light rays from that object, we could trace them all back to that intersecting point. We get a new image. Now that new image is going to be like this. I think I lost it. Here it is. It's going to be a virtual image because it's behind the mirror. It's going to be upright, and it's going to be blown up. It's going to be magnified. So if you were to imagine that concave mirror that I showed you a few minutes ago, the reason that hand looks so big is because that hand, the object, the hand, was placed at some point closer than the focal length in front of the mirror. And then you were able to see that magnified image. So those are the two possibilities for your concave mirror. You can have real images that are inverted if they are beyond the focal length. But if they are closer than the focal length, you're going to have virtual images that are upright and blown up, made much larger than the original picture, well, in the original object. So, having said all of that, that is all of the information that you need to know for the concave mirror. So let me go ahead and write that down. so that you know what we've been talking about, this is for concave mirrors. Okay, let's look at the next type now. Which is going to be like this. This one is called a convex mirror. Which is that one that gives us a wide field of view. So once again, to the left is going to be our shiny side. To our right is going to be the back of the mirror. Let's draw those lines to indicate that this is the back. And this is what ends up happening with your convex mirror. Let's draw two lines. First, this one. We draw it so that it's incident onto the surface of the mirror, and then we trace it back so that it goes through the center of curvature. That way we get a nice straight line. There's no angles happening there. Then let's do another line, another ray that is parallel to that center axis, so that when it reflects and then we trace it back, it goes through the focal point. So here we're going to have another intersecting point right here. If we do that for all of our images or all of our incident light rays coming from our object, trace them back and you'll get this image. It will always be virtual and it will always be upright. So that's pretty much all that you need to know for the convex mirror. Always going to produce a virtual image, and its image will always be upright. It will never be upside down. Nice. Okay, let's take a look at some more facts about these two types of mirrors. Let me erase this and this. Let's go over here. So I want you guys to take a look at these two comparisons for the two types. So we got your concave on the left and your convex on the right. I drew several light rays, and you see for the concave side, all of those light rays are converging or coming together at the focal point. For the convex mirror, all of the light rays are diverging. They're being bounced off in several different directions, but when you trace them back, they all intersect at that focal point. So for your concave mirror, given the fact that the focal point is in front of the mirror, it will always be a positive value. Your concave mirror can always produce a real or a virtual image, depending on where it is. So like say your object is somewhere between the surface and the focal point, it will produce a virtual image that is magnified and upright. But if it's beyond the focal point, it will produce an inverted and real image. For the convex mirror, since your focal point is always behind the surface of the mirror, it's behind, right? It would always be negative. Now, it's always going to produce virtual images because those light rays never converge in front of the mirror. So since that never happens, it can never produce a real image. It will only produce virtual images. Also, since those light rays are diverging like that, it can give you a nice wide field of view. So the convex mirror is useful for when you want to look around corners and just look around things that are kind of hard to see on your own. Okay, now let's take a look at two formulas that are important to the study. The first is the mirror equation. Sorry about that, technical difficulty. Anyway, here it is, the mirror equation. So the mirror equation is 1 over f, f being the focal length, equals 1 over dO, which is the object distance, plus 1 over di, which is the image distance. The other one is the magnification equation. The magnification M could be equal to the image height divided by the object height, or it could be the negative of the image distance divided by the object distance. So with those two equations in mind, there's one more thing that you need to see, which is the sign convention. What do positives and negatives tell us about this? Okay. First, if your image distance is positive, then it is a real image in front of mirror. Now remember, this can only be possible for concave. If DI is negative, virtual image behind the mirror. Number 3, if HI is positive, it's upright. 4, if HI is negative, inverted. Now about the magnification. If magnification equals 1, image height is equal to object height. All right, that means both things are going to be the same size, or appear to be the same size. If the magnification is greater than 1, the image is bigger than the object. If the magnification is less than 1, image smaller than object. And finally, the last two, if M is positive, you're gonna have an upright image. And if your magnification is negative, it's gonna be inverted. So those are some rules about the sign. It seems like it's a lot, but it's really not too bad. Pretty much the main ones that you got to worry about is the plus and the minus for DI and HI. The signs for M end up coming directly from the signs of DI and HI, of course. Now, your object height will always be positive because your object is always upright with respect to the surface of the mirror. And your object distance is always positive as well, because if you're going to look in the mirror, you always need to be in front of the mirror. You obviously can't look at your reflection if you're standing behind the mirror. Now, let's look at a couple of examples and be finished with this. So for example 1, we have a concave mirror that has a focal length of 10 centimeters. The question says to locate the image of a 7 centimeter long pencil that is 30 centimeters in front of the mirror. Determine the image height and whether it's a real or virtual image. And we also have to assume that the pencil is standing upright. All right, let's list what we know. Since it's a concave mirror, we know that our F is positive 10 centimeters. We know our pencil is 7 centimeters tall. And we know that it is 30 centimeters in front of the mirror. We want to determine the height of the image and the image distance. And is it virtual or is it real? Okay, let's start with DI. So remember, our equation is 1 over F equals 1 over DO plus 1 over DI. So we got 1 over 10 centimeters equals 1 over 30 centimeters plus 1 over DI. All right, so I'm going to place my 1 over DI on the left-hand side to make it a little bit easier. And what I ended up having to do was subtract 1 over 30 on both sides, right? So I'm going to do 1 over 10 minus 1 over 30. So I'm going to find the common denominator here, which is 30. And this is going to be 3 over 30 centimeters minus 1 over 30 centimeters, which is equal to 2 over 30 centimeters equal to 1 over DI. We need to do a reciprocal here because we're not looking for 1 over DI, we're looking for DI. So DI is equal to 30 divided by 2, which is 15 centimeters. Now, since DI is a positive number, that means that the image is going to be in front of my mirror, right? Which means that it is a real image. Okay, so DI ended up being 15 centimeters. No, not HI, DI. Okay, now let's take a look at the other piece, which is going to be actually, let me do this. Let me duplicate this. And then let me erase over here. Make this bigger. That's better. So, sorry about that. Let me continue what I was saying. So we now know that the DI is 15 centimeters, and we're going to use our magnification equation to figure out HI. So HI over HO equals negative DI over DO. Now we don't know what M is, so let's not worry about it. But we do know all the other stuff. So HI over 7 centimeters equals negative 15 centimeters. Actually, I don't need that parentheses. So negative 15 centimeters over 30. Now this is going to reduce to 1/2, right? So we're going to end up with negative 7.0 over 2, which is, of course, negative 3.5 centimeters. Now, the question didn't ask whether the image is going to be upright or inverted, but just for the sake of completeness, we see that this is a negative number, so it's going to be inverted. Whenever HI is negative, that means your image is going to be flipped over. All right, so that's it for that one. Now let's look at example 2. An upright pencil is placed in front of a convex spherical mirror with a focal length of 8 centimeters. An upright image 2.50 centimeters tall is formed 4.44 centimeters behind the mirror. We need to find the position of the object, its magnification, and the height of the object itself. Now remember, we have a convex mirror, which means that our focal length has to be negative. So our F is negative 8 centimeters. Now it says here the image is 2.50 centimeters tall and is going to be formed 4.44 centimeters behind the mirror. Since it's behind the mirror, it's got to be negative. And that is not going to be DO, that's going to be DI. So we need to figure out what is HO. We need to figure out what is DO. And we also need to figure out what is going to be M. Okay. Now, let's start with DO. So using our Murray equation, 1 over F equals 1 over DO plus 1 over DI. We start to fill it in. So we got 1 over negative 8 equals, you know what, I don't think we need the lines. Equals 1 over DO plus 1 over negative 4.44 centimeters. So I'm going to do the same thing as I did before. I'm going to move the DO over here to the left. And I'm going to keep this guy over here. Now what I have to do is add the 1 over negative 4.44 on both sides. We move that guy to the other side of the equal sign, it becomes positive. Now for this one, finding the common denominator is not so straightforward. So we could just do this in decimal form. 1 over 8 is 0.125, so we could do this as negative 0.125 over centimeters. 1 divided by 0.444, excuse me, 1 divided by 4.44 is going to be positive 0.225 over centimeters. That is going to give us positive 0.1. Do the reciprocal. 1 over 0.1 is going to give us exactly 10 centimeters. So there we go. Our object is 10 centimeters in front of the mirror. Okay, so let me take this one out, go over here, 10 centimeters. Nice. Now let's add another layer and let's figure out HO and M. So our magnification equation says HI divided by HO or negative DI over DO. Now, we know what DI and DO are now, right? So let's figure out what M is first. So M is going to be negative DI, so negative 4.44 over the object distance of 10. So our magnification is 0.444. Okay. And it's going to be a dimensionless number because when you divide CMs with CMs, of course, they cancel out. Okay, there's our magnification. Now let's use that to finish this problem off and figure out what is going to be HO. So M, remember, is equal to HI over HO, which means that HO is equal to HI divided by M. So our HI was what? 2.50 centimeters. Our HO, we figured out was, well, we don't know what HO is, excuse me, our M was 0.44. So all we gotta do is divide here. So 2.50 divided by 0.444, 5.63 centimeters. So there's our object height. So you place a 5.63 centimeter tall pencil in front of your convex mirror. If you place it 10 centimeters in front of the convex mirror, due to the magnification of 0.444, it will appear to be 4.44 centimeters behind the mirror and 2.50 centimeters tall. And that is it. These are basically the two kinds of problems that you'll see. Problems dealing with the magnification of concave and convex mirrors, their object and image heights, and their object and image distances, according to the two formulas, the mirror equation and the magnification equation. So there will be an assignment about this you'll see it, I'll send it out with this video. And if you have any other questions or you have any questions about this, just go ahead and send me a message on Remind. And with that, I will see you guys next time.